To complete our discussion of tensors, let me stress the difference between space and time and a few more things. So instead of dealing with space, where the metric is like this, as we already stressed, in space-time, in two-dimensional space-time, the metric is like this, dxa, dxb, where here, from now on, we assume that, for convenience, we assume that a and b are ranging from 0 to 1. What does this mean? This metric tensor has the following matrix. It's 1, 0, 0, minus 1. And as a result, ds squared is just at 1, 1 dx1 squared plus at 1, 2 dx1 dx2 plus at 2, 1 dx2 dx1 plus at 2, 2 dx2 squared. So taking into account that this is 1, this is 0, this is 0, this is 1, we obtain that this is just dx1, sorry, 0, not 1. I promised to use 0, 1, 1, 0, 1, 0, 1, 1, dx1. So this is dx0. This is 0, hence 0 squared minus dx1 squared. So this is one difference, but another important difference is now to lower and higher index we use this tensor. It means that VA is equal to eta AB VB. And similarly, we have inverse tensor BC. This is delta AC. Inverse tensor, as one can easily figure out, eta AB has the following matrix. It's the same as this one. It's 1, minus 1, 0, 0. This is Kronecker symbol, so it's 1 when A equals to C, and 0 if A is not equal to C. So using this tensor, we can do the inverse of this. So if we have something with lower index, we can multiply to this to obtain VB. So this is the rule for higher and lower indices of any tensor, not only of vectors. But there is a crucial difference now, for example, that because if VA has the following V0, V1, so it has the following components, and VA with lowercase has these components, using these relations, one can straightforwardly see that V0 is equal to V0, while V1 is equal to minus V1. As a result, for scalar product in space-time, scalar product of this form, this is a remnant of the previous discussion, so this doesn't have to do anything with what I'm saying here. Everything what I'm saying here corresponds to this metric. So if we have a scalar product of two vectors, for example, VA double VA, which is the same as eta AB VA double VB, actually the same as delta AB as VA double VB. There are many ways of writing the same expression as eta AB VA double VB. In any case, what this means, VA times double VA is the same as V0 times double V0 plus V1 times V1. But at the same time, using this relation, this is equal to V0 double V0 minus V1 double V1. And this minus sign is very crucial. Because of this minus sign, this bilinear form is invariant not under rotations, but under hyperbolic rotations, so-called Lorentzian transformations. And these are the differences we have in case of space-time. Well, the final comments that I want to make is about gradients and divergences in space and space-time. For example, well, I will do that for space-time. For example, if we have a vector xa, which is just this coordinate vector, and we can take a differential of it, for example, d over dxb of xa, which is dxa over dxb, the same. And I will use a shortened notation, dbxa. db. You see, we have the gradient carries upper index while we differentiate with the lowercase index. So it is not hard to see that this is just equals to 1 if A and B coincide, and equals to 0 if A and B do not coincide, obviously, because coordinates are independent. As a result, this is equal to delta BA, Kronecker symbol. Notice that I never use delta AB with both lowercase indices in space-time. Instead, I use eta AB. The reason for that is that this tensor is invariant under Lorentzian transformations. The inverse of it, tensor, also invariant under Lorentzian transformation. And this guy is also invariant under Lorentzian transformations. But if we have some tensor who carries both lowercase indices and whose matrix, we can denote it like this, and whose matrix has this form, under Lorentzian transformations, under hyperbolic rotations, this guy will not remain invariant. It will change so it means that delta B bar AB will not be equal to delta AB, and its matrix will be quite different from unit matrix. So one never uses this guy in space-time. In space, we can use it. In space, there is no basically difference between lower and uppercase indices. But in space-time, the difference is crucial, and it's related to this minus sign and to the fact that bilinear form is invariant under Lorentzian hyperbolic rotations rather than ordinary rotations. Now then, immediately from here appears a question, what means d over dxb of xa with uppercase, which is the same as db of xa. Well, to answer this question, let us represent it like this. db eta ac xc. But eta is constant matrix, so it's x independent, so I can take it out. This is eta ac db xc. This guy we'll already know. This guy is this guy with the different indices. So this is eta AC delta BC. But this is because it is equal to 0 when B is not equal to C, and to 1 when B equals to C. This is nothing but eta AB. Eta AB. So, as a result, we have the following relation. Well, let me write it. dAxB is delta AB, dAxB is eta AB. Similarly, dAxB is delta AB, and dAxB is eta AB. That is easy, can be easily checked. Finally, let me do few simple examples of calculations of tensor differentiation. For example, let me introduce the norm. Well, the norm I already introduced, but what it means modulus of x. Modulus of x is just square root of xa. Let us see what is this guy equals to. Let us differentiate dA of modulus x squared, which is the same as dA xb. Well, this is by Leibniz rule. This is just dA xb times xb plus xb dA xb. Well, what do we have? This is eta AB times XB plus XB times delta AB. Well, this is 2XA. 2XA. Well, this is simple exercise. Let me do a bit more complicated exercise. Similarly, if we want to differentiate modulus of x, which is already square root, we differentiate first, according to the rule of differentiations of complicated functions, we first differentiate the square root. As a result, we obtain 1 over square root of xb, and then apply the differential to the expression which stands under the square root, which is xb, sorry, let me use a different letter so that there won't be more than 2 letters coincident. Now we already know what this guy is. This is just 2xa. Sorry, there was 2 missing here, because when we differentiate square root, it's 1 over 2 square root of. So 2 over 2 modulus of x. So this is xa divided by modulus of x. So these are the simplest exercises one can do for the case of tensors. Well, one last exercise which I can do for you to clarify tensors is just differentiate 1 over modulus of x. So according to the rule of the differentiation of the square root of xb, so again, differentiation of complicated function. As a result, this is 1 over xb to the power 3/2 with a minus sign, and 2 should be present here. And then I apply the differential to the expression which is standing in the complicated function, so xc. As a result, using all these expressions, I have minus xa divided by modulus of x to the power 3.